Welcome back to our fourth video on the study of kinematics. In this video we're going to have a look at the concept of speed. So speed itself is different to velocity, such that for speed the direction is not important. Speed is increasing when v of t and a of t have the same sign, i.e. both positive or both negative. Speed is decreasing when v of t and a of t have the opposite signs. Going down. Looking at our initial conditions, or when t equals 0. Since s of t, v of t and a of t are all functions of time, then the initial conditions are found using s of 0, v of 0 and a of 0. Note, in all problems, remember time cannot be negative. That is, t is always greater than or equal to 0. Looking at some examples. Example 1. A particle moves in a straight line with a displacement function of s of t defined as 2 times t cubed minus 12t plus 1 centimeters, where t is greater than or equal to 0 and t is in seconds. Part A, find the velocity and acceleration functions of the particle's motion. So remember, what we've got is our function here defining the displacement. The velocity function is simply the first derivative of displacement. So v of t is simply the d over dt of s of t, or we can write it as s dash of t. So both of these two lines here are equivalent. So if we want, what we can say is that the function itself can be found using not first principles, or we could if we wanted to, but simple power rule. So we'll go 2 times 3 times t all to the power of 2 minus 12 times 1 times t to the 0 plus 0 because the constant is gone. Alright, so that becomes 6t squared minus 12 t to the 0, which just becomes 12. So therefore our function describing the velocity is defined as 6t squared minus 12. Now to get our acceleration function, then that's simply going to be d over dt of v of t, or we can write it as v dash of t, and therefore using simple power rule we're going to get 6 times 2 times t to the 1 minus, our 12 is going to go, its time has come, so that's going to be 12t. So part A, the function describing velocity is 6t squared minus 12, and the function describing acceleration is 12t. Now if we want to be really pedantic, then we can throw in our units, and we've got centimeters and seconds, so that's going to be centimeters per second, and this one is going to be centimeters per second squared, like so. Perfect. Now find the initial conditions and interpret their meaning. So remember, the initial conditions, where are we, are when we plug 0 into all of these functions. So let's have a look at what that would mean. If s of t, 2t cubed minus 12t minus plus 1. Okay, so the initial displacement is 1. Let's go for v of t, or v of 0. So what we find is that at v of 0, or at t equals 0, the velocity is minus 12. So that's centimeters, and this is at centimeters per second. Then finally our a of t. Alright, so looking at this, what we can see is that at t equals 0, the particle is at 1 centimeters. The particle is at a displacement of 1 centimeters from the origin. Okay, similarly, the velocity itself, the particle has a velocity of, particle starts with a velocity of negative 12 centimeters per second. And the particle it's undergoing an acceleration of 0 centimeters per second squared. Alright, drawing a sine diagram in the second part. What we're going to find is that for the sine diagram of v of t, since v of t is defined as 6t squared minus 12, what we can do is we can factorize for the 6, so it will be t squared minus 2, and then we'll do the roots here. So the roots of this particular one are going to be 6t plus root 2, t minus root 2. So it's a perfect square sort of, difference of two squares condition here. Even though 2 is not a perfect square, we can make it, we can still trigger the condition by taking the root of 2. Alright, so for the sine diagram of v of t, we know that it's got to start at 0 because remember we can't get negative time, at least in this context. And we're looking at the values of v of t either side of root 2. So what we'll find is that if we plug in, say, 1 into this equation here, what we'll find is that when we put in a value of 1, we find that the output is going to be negative. So this term here is going to overwhelm the 1 and everything will swing negative. Now if we put in a value above root 2, then again this value here will become positive. So what we'll see is a positive value here. So what we in fact find is that from before t equals root 2, the particle is moving to the left, and then after t equals root 2, the particle starts moving towards the right. Alright, moving down into a of t, that's defined as 12t, so nothing to factorize here. And then the sine diagram, looking at this, for the sine diagram of this, for all values of, actually I should put this in 0, for all values of t greater than 0, or all valid values of t, we're going to see positive values. So what we can see is that acceleration is increasing from the initial point in time 0. So it's it's accelerating infinitely. Alright, moving down. We're looking at the analysis of the results we saw up above. So again, at what times is the particle's speed increasing? Well, for this particular question here, we have to look at the sine diagram. And remember, at the very beginning we said, let's go up a little. Where are we? Okay. Speed is increasing when v of t and a of t have the same sign. So what we need to do is look at the sine diagrams and look at when the signs are positive or the same. So in this case, the acceleration, it's always positive, but it's when the velocity is also positive. So what we find is that speed is increasing. Speed is increasing when t is greater than the value of root 2. Because remember, it's from there onwards, that's when we see an increasing, because that's when both of the signs are both positive. If they happen to be both negative at some point in time, then we'd see it increasing in the negative direction, but in this case it's only positive acceleration. Alright, looking at part 2. At what times is the particle's velocity increasing? So to do this sort of question, firstly, we have to look at the acceleration. Notice that the acceleration is defined as 12t, and therefore, when t is greater than 0, the particle is accelerating in the positive direction. Now, looking at the velocity, what we can see is that before t equals root 2, the particle's actually got a negative velocity, which is suggestive that it's moving towards the left. But because the particle is always undergoing a positive acceleration, that means between t equals 0 and root 2, the particle is becoming less negative in its velocity. And therefore, the velocity itself, even though we're negative in this 0 to root 2, it's still increasing in value. Similarly, when we hit t equals root 2, the velocity is stationary, or the velocity is equal to 0. And as t equals or is greater than root 2, the velocity itself is increasing. So by that definition, what we understand is that the velocity is always it's always increasing from when t is greater than root 2. So when t is greater than 0.